Draw a labeled free body diagram showing the forces acting on Paul as he sits at rest. So he's obviously got a weight acting downwards. And if we're drawing a free body diagram, Paul turns into a circle. We then are going to have, he has obviously got a normal force. That's easy. Now we need to decide what is the force that's holding him up the slope. Sometimes it's friction, sometimes it's a rope. What does it say? He sits on a rough rock, so that must mean it is friction. Do not add any other forces in. You may need them for calculating, but that is your force diagram. If you go and put the components of weight in, you land up double representing weight, and that's incorrect. Calculate the magnitude of the gravitational force on Paul. That is going to be his weight, and weight is just equal to 80 times mass times 9,8 the acceleration, and you land up with an answer of 784 newtons. Calculate the magnitude of the frictional force. Okay, so now what we're going to do is we're going to bring a force down here, and that's going to be equal to the normal, and we're going to have, now I'm doing a calculation. Okay, this is not my force diagram any longer. That's my friction, that's my normal, and here's my 30 degrees. Okay, and I'm interested in the frictional force, which means it is the opposite side, and I know that this side over here is 784. So I am going to say sine, so force is equal to, or rather I go sine of 30 is equal to the frictional force divided by the weight, which is 784. And I find that the frictional force will turn out to be equal to 392 newtons. Calculate the magnitude of the normal force that is exerted. This time I'm looking at the adjacent side, so it's cos of 30 degrees is equal to the normal divided by 784, and the normal turns out to be equal to 678,96 newtons. Dylan tells Paul that the coefficient of static friction between Paul and the rock is 0,62. Use a calculation to test this. There are two ways you could have done it, but I'm going to show you the one way. The frictional force is always equal to the coefficient of friction multiplied by the normal. So that is going to be equal to 0,62 multiplied by 678, as I've calculated it, 96, and I get 420,96 newtons. That is not equal to 392 newtons, and therefore Dylan was wrong. You could have done it the other way around, where you worked out what the coefficient of static friction was using these two numbers over here, and in doing that you may have found that you will have got a number that was different from 0,62. Remember, static friction is when something is stationary, whilst dynamic friction is when something is moving. A pulley is often used to help lift heavy objects, as shown in the diagram. We've got a 50 kilogram block, 20 kilogram block, and they're being accelerated upwards. State Newton's law of motion. So that is bookwork. You just need to state it. When a net force acts on an object, it accelerates in the direction of the net force. The acceleration is directly proportional to the net force and inversely proportional to the mass of the object. State the tension in rope A. You don't even have to calculate it. It's one rope over a frictionless pulley. So rope A is 950 newtons upwards. It needs to have a direction. Why does it need to have a direction? Because it is a tension, which is a force. It doesn't say magnitude, so you have to give it a direction. Two separate labeled free body diagrams. The first one has weight acting down. Obviously, you're going to draw this as a dot. And it has a tension acting up. We'll call it tension B. Then, if I take a look at the 50 kilogram block, it will have a weight acting downwards. It will have tension A acting upwards. And it also has tension B, sorry, there's a bit of a space shortage, acting downwards. They are represented with circles, and the arrows go away from the bodies. Then we have to calculate the acceleration of the system as well as the tension in rope B. So we are going to say force resultant for, I'm first going to worry just about the 50 kilogram block. Force resultant is equal to big force. Obviously, this whole system is moving upwards, so we're going to call it tension A, minus the small forces, the weight of 50 kilograms, and tension B are both acting downwards. I can put a whole lot of information in. This is 50 times the acceleration of the system. This is 950. The weight of a 50 kilogram object is 50 times 9,8, so it's 490 minus tension B. Now I say what is happening over here with tension with the 20 kilogram block. Separately, I look at the force resultant is equal to the big forces, which is, it's going upwards, so it's tension B, minus the small force of the weight of the 20 kilogram block. And I then say tension B is, I don't know, 20A, and the weight of a 20 kilogram block is 20 times 9,8, which is 196 newtons. I then simultaneously solve those two equations, and I find that I get that A will turn out to be 3,77 meters per second squared, and when I substitute it back in, the tension in B turns out to be 271,4 newtons. We've got a block, and it's released from rest at a certain height on a frictionless 30-degree incline as shown. It slides down the incline and along the frictionless surface until it collides elastically, important, with a 0,8 kilogram block at rest at 1,4 meters from the bottom of the incline. Define mechanical energy. Later on, it's going to ask us to state the law of conservation of momentum and define an elastic collision. All of those are bookwork, and you need to get those right. So looking at those definitions, we have got that the mechanical energy is the sum of the gravitational potential energy and kinetic energy at a point. That the law of conservation of momentum, total linear momentum in a closed system stays constant. An elastic collision, a collision in which both momentum and kinetic energy are conserved. Calculate the gravitational potential energy of the 0,2 kilogram block, I suppose, as it is released from rest at a height of 25 centimeters. So I need to say potential energy is equal to mgh, which is equal to 0,2 times 9,8 times the height needs to be converted into meters, 0,25 meters, and I'll end up with 0,49 joules. Calculate the magnitude of the velocity of the block as it slides along the horizontal surface. That will be exactly the same all the way. Because this is a frictionless surface, I'm just going to work out what happens as it gets down to the bottom. So the kinetic energy at the bottom is equal to 0,49, which is equal to a half of m, which is, what was the mass of that block? 0,2 multiplied by v squared, and the velocity turns out to be 2,21 meters per second. Then it says, why does the velocity of the 0.2 kilogram block remain constant along this 1,4 meters horizontal surface? And you must refer to one of Newton's laws in your answer. There is no friction on the surface. Therefore, there is no unbalanced force in this object on the surface. So, an object will remain at rest or in a constant state of motion in the absence of any unbalanced forces. So that is what happens over there. And it's Newton's first law that you are referring to. The next two we've done, and then calculate the magnitude of the velocity of the 0,8 kilogram block immediately after the 0,2 block collides elastically with it. So now this is quite a long and detailed process. Let's go through it. I need to firstly say what happens with momentum. The momentum before is equal to the momentum after, and remember you have to state these things. Then you're going to say 0,2 was going at 2,21 before the collision, the other block was standing still, is equal to 0,2 V1. No one said that they stuck together, plus 0,8 V2. Now we have got a simplified equation that looks something like V1 is equal to 2,21 plus 4 V2, and we land up with doing another one, kinetic energy before is equal to kinetic energy after, and therefore I'm going to say a half of 0,2 2,21 squared is equal to a half of 0,2 v1 squared plus a half of 0,8 v2 squared. When I solve these simultaneously, I find that v2 is going to turn out to be equal to 0,88 meters per second.